Hi, I'm Coach Cowland, and in this presentation we're going to be looking at graphing motion. So we use a lot of graphs in science to basically look at and evaluate data. We use them to find relationships, find patterns, to visualize data that we found from experiments, and we use them in all areas of physics. They're really important, and it's one of the things that you look at in physics in high school, in college, and if you go on to research, that's one of the things you'll spend a lot of time on is just looking at graphs. So specifically to graphing motion, I want you to think about a couple of things. What variables can you graph? What variables should you graph when you're graphing things? What's important and what's significant, and what do we want to know about? Those are the things that we need to think about when we're sort of determining graphs. There's no use having a graph that plots two variables that we don't care about. And then when we know what variables we want to use, we need to determine where would we place the graphs, the variables on the graph. Which one should we use on the x-axis? Which one should we place on the y-axis? Because we want them to be put in a useful way and a way that's going to be helpful in extracting the data that we need. So that's another important aspect. The third thing is sometimes we can take various different bits of data from the same bit of information that we've found, and some of them will be useful for some things and others will be useful for other things. This is true of motion. We can take several bits of information, we can graph several different things for any motion that we graph. What graphs could what things could we graph when we are graphing motion? I want you to have a think about those things, and I would like you to write them in your notes when you're taking notes for this presentation. Okay, so one of the things that we could do is we could look at distance and time. We could graph distance and time if we wanted what? Yes, if we wanted to look at the speed, we would graph distance and time. Because distance divided by time gives us speed. And there's a reason for the way that we put distance on the y-axis and time on the x-axis. And the simple reason is that if we want the slope of a line, we do the rate of change of y divided by the rate of change of x. And in this case, the slope gives us the speed. It's a really easy mathematical correlation from one to the other. The slope of the line between any 2 points gives us the speed between those 2 points. So there's 2 points here, point A and point B, which are on the graph, and taking those two values, you can calculate, taking those 2 points, initial and final, you can calculate the speed between those 2 points. The average speed, if you were to be specific. Now, because this is speed, direction is not described in this. It's just the speed. And just like when you're going down the road in your car, you look at your odometer, it tells you you're going at 30 miles an hour, then you're going at 30 miles an hour. It doesn't say that you're going north at 30 miles an hour unless you have a very fancy car. So instantaneous speed, a little bit different. Same graph though. You can see that the instantaneous speed at point A and point B is different. And the way that we work those things out is that we take a tiny little slither of that graph, if you like, and then we take a tangent to it, and you can see that the red arrow is at a tangent to point A and the green arrow is at a tangent to point B. So those two are the instantaneous speeds at those two different points on that graph. Now on this graph, the instantaneous speed at point A would be exactly the same as the average speed that we worked out on the previous slide. The instantaneous speed at point B though would be different. So here we have a slightly different graph. This is a displacement time graph. The difference between a displacement time graph and a distance time graph is that the distance time graph is used to calculate speed and a displacement time graph is used to calculate velocity. Another important aspect of this is that we have this area here. Now, we said when we looked at distance and time that your speed can only ever be positive. You'll never get a negative value on your odometer. You'll never be traveling at negative 30 miles an hour. So getting a distance that would be negative, a negative distance time graph wouldn't make any sense at all. Okay, how could you have traveled a negative distance? Yesterday I went for a walk for negative 5 miles. I don't think that that really makes any sense, right? Um, so there's a significant difference there between distance and time, even though it is subtle. Now we have five aspects of this graph that we're looking at. There's the green line, the red line, which actually changes, and then there's this curved blue line, which is a little unusual. What do you think is going on for each of these lines? We'll go through one by one, but I want you to have a think about it before we do. Okay, are you ready? Okay, the first line, number one. You can see that this is a straight line. So what does that tell you about the change in displacement over time? It tells you that it's constant. And if the change in displacement is constant, then you have a steady speed, or steady velocity in this case. It should say velocity, not speed, right? But you can also see that it's a pretty steep line, so it's quite fast. And if you compare that to aspect number 2, which is part of the red line, you can see that that line isn't as steep. So if the slope is less, then the velocity is less. So it's steady and constant velocity, but it's less than the velocity of the green line. Now, what do you get when you get a horizontal displacement, or even a horizontal distance in a distance time graph or a displacement time graph? Well, the displacement or the distance is not changing. So if the displacement or the distance is not changing, what's happening to the object? The object isn't moving. So the object is stationary for that period of time. So you can see that there are, say, 4 squares, which are the time units. So over that point, the object stays in exactly the same place. Now we'll come back to part 5, which is the negative displacement, in a minute. Let's have a look at part 4. Now this one is much more complicated than the other parts that we've so far looked at. And how are we going to solve this? Well, in order to do this, we need to look at the instantaneous speed at the different points. So if I took if I looked at the tangent of the line here, the instantaneous speed here, it would be not very steep. And if I looked at the instantaneous speed here, it would be a little steeper. If I looked at the instantaneous speed here, it would be steeper still, and steeper, and it would continue to get steeper. Now we said that the instantaneous speed was the speed, or the instantaneous velocity, I should say, is the velocity at that instant. So the velocity is changing at all of these instants. So if velocity is changing, what's happening? It's accelerating. It's getting faster. In fact, in this case, the acceleration is in the same direction as the motion. So it's getting faster. Now for section number 5, the displacement is decreasing. And if we graph a line and we have a decreasing displacement, a decreasing y, as an increasing x, we end up with a negative value for velocity. And if the velocity is negative, that means that it's going backwards. So it's returning to the start. Now the rate of this negative value is different to the rate of the positive value. You can see that the positive part takes 3 time units, the negative part takes 2.5 time units, and that means that it's a negative with an absolute value which is greater, which means that it's going back at a quicker speed than it started with. So this object which we graphed with the red part, it's going to a place, it's staying still, and then it's going back a little bit faster than it started. Now there's one type of motion that I haven't included here, and I'm not going to tell you about, but I want you to have a think about it. How would I graph an object that is slowing down? It starts at a constant velocity and it is slowing down at a gradual constant rate. In some respects you might say it's decelerating. Physically we would talk about it as a negative acceleration. What would that line look like? Have a go, put an estimation of that in your notes, and we'll have a look at that and discuss it in class. So this is just a quick review of displacement time graphs. With a displacement time graph, you're looking at the rate of change of x over the rate of change of t. The final position minus the initial position divided by the final time minus the initial time. And the slope of that graph gives you the velocity, which can be negative. Another type of graph that we could look at is a velocity time graph. So this is a graph which looks at the rate of change of velocity divided by the rate of change of time. Again, it can be positive or negative. Now, in this graph there are three sections. The first part, you can see this is a pretty steep line, so this means that there is a pretty steep positive acceleration. That means that the acceleration is in the same direction as the motion. The second part here, there is no acceleration. This does not mean there's no movement. You can see that the velocity is actually 20 meters per second, so it's moving pretty fast. What it means is that it's not getting any faster. And then in the third section here, part C, the acceleration is negative, but it's not quite so negative as this is positive. So this means at this point it is accelerating in the opposite direction to the motion, or slowing down. Now, there's another bit of information that we can get from this velocity time graph other than the velocity and the acceleration. The acceleration we find by the slope. The velocity we can find by just looking at the y-axis, but we can find something else that's really important. When you're looking at a graph, what other piece of information is easy to ascertain? Have a think about that before you move on to the next slide. Okay, did you have a think about it? Did you get it? The area under the graph. What does the area under the graph give you? Well, if you look at the units, the y-axis is meters per second and the x-axis is seconds. If you multiply the units together, what do you get? You get meters. Meters is a measure of length, and length in this case would give you your displacement. So this graph is actually really useful. It tells us how far something's traveled, it tells us how fast it's going at any point, and it tells us what the acceleration is at any point as well. So if we have a velocity time graph, we can do an awful lot of stuff in motion. Really good, and we're going to use them an awful lot. So one final question before we stop. What type of graph haven't I talked about? There is one more at least. So I want you to have a think about that. What variable have I not had on one of these axes that probably should be there? It should be on the y-axis. It should be instead of velocity or instead of displacement or distance. So have a think about that and put your estimates on your notes. Okay? Thanks for watching.